As you mentioned, I'm Derrick Quinn. I work with Dr. Elian. I'll be presenting my project, Near Memory Acceleration of Retrieval Augmented Generation. I think in the original title, it was Retrieval Augmented Machine Learning, but generation, because we focus on specifically large language models and generative AI here. So I'll go over sort of what I'll cover here. First of all, we have, I'll motivate a need for retrieval augmented generation in the first place by covering the disadvantages of traditional large language models and generation, specifically problems with parametric knowledge. Then I'll explain what exactly RAG, or retrieval augmented generation, is. I'll explain how retrieval works. And then I'll go through the profiling of a RAG pipeline. Right, we have constructed a representative RAG pipeline. And then I will look at software alternatives to traditional RAG, specifically approximate nearest neighbor, that can speed things up. And then I will conclude that RAG has performance issues and look at accelerating it in hardware with XRAG, or accelerated retrieval augmented generation, and an intelligent knowledge store, which is a memory expander with near memory compute, designed to accelerate these workloads. All right, so to start with, large language models, specifically transformer-based large language models, have brought significant improvements, especially for natural language processing. They are now the state-of-the-art for NLP tasks, and arguably they were always the state-of-the-art for NLP tasks as soon as they were released. I'll look at translation and text generation. In the paper that proposed the transformer, attention is all you need, immediately it was achieving state-of-the-art results as far as translation and generating text on a compute budget. And this has been absolutely critical. There'd be no ChatGPT or anything like this without the transformer. However, they memorize information, and this is a pro in some capacity because you can ask them questions and they know things. But it's actually where I'll be focusing for this, because there are issues with memorizing information. Right? Terminology here, we call this parametric knowledge. It's knowledge memorized into the parameters of a large language model. That's why parametric. And some of this, like I said, some of this is very good. Some things are worth memorizing, specifically rules of a language. Syntactic rules are important to memorize, but there are issues with this as well. For example, hallucination is a problem because all of the knowledge is parametric and it's inextricably linked to the rules of the language. Models have no idea what they do or don't know, which leads to hallucination. And secondly, there's issues with retraining and fine-tuning, because whenever you need to update the knowledge of the model, you have to go through this retraining process, and that is potentially, depending on different model architectures, very expensive. I think, generally speaking, very expensive. And it's also not as simple as just updating it on new knowledge. You have to potentially do a lot of retraining on stuff that you've already covered. And for temporal data, even if you can retrain, if you can afford to, retraining can take so much time that it's impractical for information that is just coming out. Like, you can't really retrain within the hour a lot of the time. And so to solve these problems, we'll have a retrieval augmented generation, right? The idea here is that we have a database that we augment this LLM with that will find relevant data. There's a illustration of it here on the right. The idea with this is that we'll be able to update knowledge easily, and that because we'll have some semblance of some idea of whether or not a piece of knowledge is in the database, we can potentially reduce hallucination with this, potentially significantly. But I'll cover sort of how this retrieval works, because it's important to the rest of this. But yeah, this retrieval augmented generation is a significant step forward. And in fact, I don't think I mentioned this here, but nowadays all of the exciting large language models do some sort of retrieval augmented generation, or RAG. GPT-4 on Bing does it, Bard does it. GPT agents rely almost like exclusively on retrieval, so it's very important. But anyway, the way this works is that there's some deep retrieval model that's trained to identify relevant passages. So you've got a prompt and a passage embedded somehow, and this model will, the way that those embeddings are created, it's trained to identify which passages are relevant. I'll go through exactly how this works, though. Yeah, like I said, we can compute embeddings for the corpus and the prompt, and then once we've got these embeddings, we compute a dot product to determine the similarity score. So the way this works, imagine for a second that this tokenizer is trained. I'll go through how it's trained in a second, but we'll get a prompt, which is just plain text. It will be tokenized, converted into a large high-dimensional vector. In our case, for our pipeline that we tested, it was 768 was the dimension of the vector, but it's something large. Then this dot product, so we'll compute those embeddings for every single passage in a corpus as well, and then compute the dot product between that prompt, which is Q, and each of the n corpus vectors. So then we have n similarity scores, but we don't want to look at all of the documents in the corpus. We just want the top certain amount, probably 10. So like Google search has the top 10 that it shows you. Similarity here. That number is k, much smaller than n, and we select those k. This is exactly k nearest neighbors, by the way. And then those corresponding passages that have the highest similarity scores are then sent to a generator, which is just a large language model, and this is just presented as context. So we want to test, we want to profile this and see where the bottlenecks are with this, with retrieval augmented generation. So we put together a representative RAG implementation. The corpus here was Wikipedia, was just a dump of Wikipedia, like the passages of Wikipedia. This is specifically a question answering large language model that is then going to use Wikipedia to generate its answers, essentially. The retriever model is a deep retriever trained on this meta-kilt NQ train data set, and generator is a Google T5 model also trained on NQ train. NQ train is a data set that contains essentially like a 3-tuple of a prompt, relevant passages, and a correct answer. So you can train the entire RAG pipeline with it. And then we look at running this pipeline on various different hardware topologies. So I'll mention a CPU, which is just general purpose CPU cores. This has AVX, so we can take advantage of AVX compiler optimizations, but not AMX. And AMX is Intel's new on-chip matrix multiply accelerator, pretty good for machine learning. And then GPU, we use a single NVIDIA A100, the 40 gigabyte version specifically. And we look at running the retriever and the generator on each of these different topologies. I don't include data for running the retriever on AMX, but I'll mention what the shortcomings of that are. So in the interest of time, I'm not going to go through all of these nitty-gritty results here, but when we do the search, the retrieval phase on the CPU and the GPU for generation, right? GPU for generation is the way that it's done typically. You have these GPUs for doing inference on large language models. If you use the CPU for search, it takes too long. We have this is okay. On the right here, this is I showed just CPU inference. When we're just doing CPU inference, CPU generation, the black bars here correspond to search time. The white bars correspond to generation time. And this is the passage count. This is that K value. We look at a latency optimized and a throughput optimized batch sizes. What this is saying here, when you combine with GPU generation, that's this. GPU inference, when we do GPU inference, the black bars are a lot larger than the white bars, which is saying that the GPU generation time is very fast, but the CPU search is very slow, regardless of the configuration. Well, we can accelerate the search phase using our existing accelerators, specifically AMX and GPU. GPU does provide a massive speedup, but it has issues. I'll get into what exactly those are, but the big one is cost. I also claim that the GPU is suboptimal for this task. I'll get to why that is exactly. The near CPU accelerators like AMX do provide a speedup, but it's not a huge speedup, like 45%. I'll get to why. And then there's approximate search schemes. I won't go through all of the results here, but they aren't good enough because they cause an accuracy drop. you address that accuracy drop by using more passages, and using more passages drives up the generation time more than you save search time, right? And well, the problem with this is that the CPU search is memory bound. And this is actually why the GPU is so much faster. GPUs have faster memory, but then they end up being memory bound as well. So we have all of this compute on the GPU stranded. And the same thing happens with on-chip on CPU accelerators and even the CPU. So the search phase is very memory intensive, even though it does actually just boil down to a big matrix multiply. Because we're only using each of the input vectors once, it's memory bound. So if we can't fix it in software and the existing accelerators aren't good enough, we look at, we need to move this compute closer to the memory to speed up this process. To solve this, we build a accelerated exact search pipeline, right? And this needs to do a few things. It needs to have efficient and fast dot product computation. Like I said, it's a memory intensive process. It's a data intensive process, but we still need to be able to do the compute efficiently and quickly. And we also need a massive storage capacity. One thing I didn't mention is that we weren't actually able to test the GPU for the search phase because it didn't fit. Our corpus doesn't fit on a single GPU. And given the cost of these GPUs, that's an issue. So we need to have large capacity, and that large capacity needs to be relatively cheap. I'll get into that in a second. And memory bandwidth needs to be high to solve that data intensive problem. And we need to do this while provisioning compute and memory bandwidth in sensible ways for this retrieval process, right? We don't want to have too much compute or too much memory bandwidth because then we're spending money on nothing, essentially. Right? And we do this with this hardware accelerator that we built, that we designed, called the Intelligent Knowledge Store. It is attached over cxl.mem. For those of you who aren't familiar, CXL is just a PCI Express wrapper that allows you to communicate in a memory transparent, cache coherent way to a PCI Express memory, PCI Express attached memory. So this is essentially just a PCI add-in card, right? That has 10 ranks of DDR5 7200. DDR5, by the way, is a lot cheaper than the GDDR5 that you have on GPUs. So that's a lot of the appeal of this. Each one of these ranks has a near memory accelerator, right? That can access the DRAM chips directly without going through through the entire memory subsystem. These will store our queries that we have in a batch. It will do all of the dot product calculation to compute the similarity scores, and it has a memory controller to load to control these DRAM chips. And then it will also do the top K aggregation in hardware. That's what I cover here. The top line figures for this is total memory bandwidth of 576 gigabytes per second, which is substantially in excess of what you get from CPU to host memory. Total capacity of 640 gigabytes, which is a lot bigger than what you get on a GPU. And total compute of 1280 gigaflops per second, which is very modest, actually. But like I said, this is a data-bound pipeline, not a compute-bound pipeline. And by using this compute efficiently, this is actually enough. We don't need any more than this. And like I said, most notably, it's DDR5, not GDDR5. It's a lot cheaper. It's a lot more power efficient than you get on a GPU. To evaluate the near memory accelerator, we implement it in Verilog, gathered data for area, power, and timings from Genus synthesis solution for a 45 nanometer node. And we developed a cycle approximate simulator to evaluate the entire pipeline. And what we find is that XRAG with the Intelligent Knowledge Store enables a significant end-to-end improvements. It's like 3.5 to 5.5x. I don't know if I list that here, for various batch sizes, yeah, various batch sizes. Just some graphs here. So we compare throughput versus accuracy for a lot of different configurations. The first being just basic CPU search and GPU generation, basic thing. And then we look at different passage counts. More passage counts take longer to process, but provide higher accuracy. Essentially, you want to go top right here, more queries per second and higher accuracy. Using an approximate nearest neighbor search causes, right, you get a lot better throughput, but then the accuracy doesn't scale as well, and it eventually ends up being suboptimal, like I mentioned earlier. We tested this for several approximate search schemes, but we just list two here because these are the best two that we could find. This is for a much larger parametric only language model, this plus here. And it's faster than a RAG pipeline just because it doesn't have to do the search phase, but its accuracy is lower and fixed. And then with XRAG, we have the same accuracy essentially as the CPU search and GPU generation. It's deterministic, but it's significantly faster. And like I said, depending on the configuration, it's 3 to 5.5x faster. Here's the time breakdown. Where are we on time? Okay, the time breakdown. This on the left here, we have the accelerated retrieval augmented generation with GPU inference, and on the right, it's CPU search with GPU inference. As you can see, we massively, across all these configurations, reduce the amount of time spent on the retrieval phase. Obviously, generation's unaffected, but the end-to-end, we do see a significant improvement in throughput. And here's just like tuning of the provisioning of compute and memory bandwidth. For smaller batch sizes, it still ends up being memory bound, right? And so we have we're spending a significant amount of cycles inside of the IKS stalled on reading from memory. But then as the batch sizes get larger and we have to do more computing and more computing relative to how much we're reading, the pipeline is between 2 and 3 balanced, and we have a perfectly balanced amount of compute and memory bandwidth. But then past that point, we are bound by compute. So in conclusion, went over the problems with parametric knowledge only for large language model inference. Covered why RAG is popular to address these issues, and then sort of covered why RAG has issues that are pretty hard to solve at the moment with the current available hardware and software, and then looked at how we can solve these problems by moving compute closer to the memory to address that data intensive operation. I think this is the last slide. This is based on a paper that we are submitted to the International Symposium on Computer Architecture. We find out soon whether or not it's in, but yeah, that's all I got. Any questions?
Any questions for Dave?
Yeah.
So this is pretty incidental, but can you go back to slide 8? I think this is actually in previous work, but I wasn't quite sure what the numbers were in the middle of the paper. You're going to seem to indicate that higher is better, but
right, yeah, higher is better. I should have. So BLEU is a score that they use to evaluate translation. In this paper, I don't exactly remember what it stands for. Higher is better on this. There's also, I didn't include it on the right here. They also cover like training time, and training time is significantly lower for the transformer as well. But yes, higher is better. I can find exactly what BLEU means though.
I got it.
Okay.
Any other questions?
Anything else?
Maybe I'll ask the same question I asked. I mean, what do you feel like is the most significant contribution to this?
So this is the latest paper in a long line of papers, kind of demonstrating that a lot of the operations that we're trying to do nowadays, more and more with computing, is data intensive and not compute intensive. And that's a logical conclusion of the memory wall. The fact that memory speeds are not changed that significantly in the past 10 years, but compute is 1,000 times faster for machine learning tasks. It's just kind of, it's what happens. And this is yet another motivation towards moving compute closer to the memory. This sort of memory expander has been proposed before, just not in this context, essentially. Yeah.
You earlier mentioned software solution, I think. So if you might talk, speak.
Sorry, what?
Like, could you? I don't know if you mentioned it, like part of the methodology and evaluation session, but how does that compare to SRS?
So I mentioned that at the end, I show the end-to-end results. The approximate search schemes, they do that's this X and the square. These are the two best ones that we could find. They are faster than XRAG. The problem with them is that the results that they bring back aren't quite good enough, and so you need to bring back more of them to reach the same level of accuracy, and then that adversely affects your generation time. So much so that your end-to-end pipeline isn't as fast then as a more accurate exact search model. Yeah.
At the very end, you had the medical being like 5.4x performance.
Yeah.
So what, like in real terms, does that buy one?
So that's well, it's in raw numbers, it's just 5.4 times the throughput of the entire RAG pipeline. That's time, you know. It's also we didn't look at it, but there's like an energy savings there as well. And another thing I didn't even mention here that there's so much that we covered in the paper that's hard to cover here is there's also scalability. Our sort of argument here is that by doing this in hardware with this sort of accelerator for near memory computation, it buys you a lot of scale. Essentially, you can do this at a far larger scale than you could before.
Thank you.